Welcome to Sleepless Philosophers, where deep ideas meet restful nights. If you enjoy these journeys through philosophy, please like and subscribe and turn on notifications for daily uploads. To support the channel, consider leaving a super thanks. Any amount helps us continue creating content. You can also become a member to request video topics. We're not monetized, so your support truly makes the difference. Now let the philosophy begin. Newcomb's paradox. A being with perfect or near-perfect predictive abilities presents you with two boxes, one transparent and one opaque. And the rules of the game are simple, but the decision is agonizing. And this is Newcomb's paradox, a thought experiment devised by physicist William Newcomb and popularized by philosopher Robert Nozick that has divided decision theorists and philosophers into rival camps for decades. The transparent box contains $1,000, visible and certain, while the opaque box contains either $1 million or nothing, and the amount depends on a prediction made by the being before you arrived. If the being predicted you would take only the opaque box, then it placed $1 million inside, but if it predicted you would take both boxes, then it left the opaque box empty. The being has made this offer to many people before, and has never been wrong. Its predictions are accurate with such consistency that it seems to know the future, or at least to understand human psychology so deeply that it can foresee choices with near certainty. Now you must decide, do you take only the opaque box, trusting the prediction and hoping for $1 million? Or do you take both boxes, reasoning that whatever is in the opaque box is already determined, and you might as well collect the extra $1,000 from the transparent box? The paradox arises because two different principles of rational decision-making give opposite answers, and both seem compelling. The expected utility calculation favors taking only the opaque box, because if the being is almost always right, then taking only the opaque box gives you a high probability of receiving $1 million, while taking both boxes gives you a high probability of receiving only $1,000, and so the one-box strategy maximizes expected value. But the dominance principle suggests taking both boxes, because at the moment you make your choice, the contents of the boxes are already fixed. The being has already made its prediction and either placed the $1 million or not. And since the past cannot be changed, your decision cannot affect what is in the opaque box. And therefore, taking both boxes gives you $1,000 more than taking only the opaque box. No matter what the opaque box contains, and dominance reasoning says you should always choose the option that does better in every possible state of the world. The paradox forces a choice between two deeply held intuitions about rationality: the idea that rational agents should maximize expected utility, and the idea that rational agents should not leave money on the table when doing so cannot possibly make things worse. Philosophers and decision theorists remain divided. Some are one-boxers who argue that the being's predictive accuracy makes the dominance reasoning irrelevant, that the correlation between your choice and the contents of the box is so strong that you should act as if your decision causally affects the prediction, even though temporally it does not. While others are two boxers who insist that causal reasoning demands taking both boxes, that the prediction is already made and your choice now cannot retroactively change it, and that one-boxers are falling prey to magical thinking, confusing correlation with causation. The paradox also touches on issues of free will and determinism, because if the being can predict your choice with perfect accuracy, then in what sense is the choice free? And if the choice is not free, then what does it mean to deliberate about it? And if determinism is true, does that undermine the concept of rational decision-making altogether? Newcomb's paradox has inspired the development of new decision theories, including causal decision theory, which endorses two-boxing, and evidential decision theory, which endorses one-boxing, as well as more exotic approaches like timeless decision theory and functional decision theory, which attempt to handle cases where agents can predict or simulate each other. The The paradox remains unresolved, a strange meeting point of probability, causation, choice, and prediction. A puzzle that reveals how little we understand about what it means to decide, and whether the principles we use to navigate an uncertain world are as solid as we believe, or whether they crumble when pressed against beings who can see through us, who know what we will do before we do it, who turn decision-making into a game where the rules themselves are in question. More's paradox. The philosopher G.E. Moore identified a peculiar class of statements that seem absurd or irrational to assert, even though they may be true. And these statements take the form, "It is raining, but I do not believe it is raining," or "I believe it is raining, but it is not raining." And these statements, while not logical contradictions, strike us as deeply strange, as something no rational person would say. And this strangeness is More's paradox, a puzzle about the relationship between belief, assertion, and truth that has implications for epistemology, the philosophy of language, and the nature of self-knowledge. Consider the statement, "It is raining, but I do not believe it is raining," and suppose this statement is true. It really is raining, and the speaker genuinely does not believe it. Perhaps they are looking out the window, but not paying attention, or they are in a state of denial. And so the two conjuncts are both true, and there is no logical contradiction. The world can be such that it is raining, and such that someone does not believe it is raining. And yet if someone asserts this statement, if they say out loud, "It is raining, but I do not believe it is raining," the assertion seems absurd, self-defeating, almost incoherent. And the absurdity does not lie in the content of the statement, which may be true, but in the act of asserting it, in the pragmatic dimension of language use. The paradox arises because assertion carries an implicit commitment to belief. When someone asserts that P they normally implicate, even if they do not explicitly state that they believe P, that they take P to be true. And so, asserting it is raining implicates that the speaker believes it is raining, but the second conjunct explicitly denies this belief. And so, the assertion, as a whole, both implicates and denies that the speaker believes it is raining. And this creates a pragmatic contradiction, a clash not between the truth conditions of the statement, but between the commitments carried by different parts of the assertion. Ludwig Wittgenstein famously analysed More's paradox, arguing that it reveals something important about the grammar of belief, about the way belief and assertion are related. And Wittgenstein suggested that saying, "I believe P," is not a report of an inner mental state, not a description of something going on in the mind, but rather a different way of asserting P, a way of committing oneself to P with a certain degree of caution or tentativeness. And if this is right, then I believe it is raining, but it is not raining is paradoxical because it both asserts and denies the same thing. It commits to the truth of the proposition while simultaneously withdrawing that commitment. Others have analysed the paradox in terms of rational constraints on belief and assertion, arguing that rationality requires a certain coherence between one's beliefs and one's assertions. That if you assert P, you should believe P, and if you believe P, you should regard P as true. And so, asserting it is raining, but I do not believe it is raining, violates these coherence requirements. It displays a kind of epistemic irrationality, a failure to properly integrate one's assertions with one's beliefs, even if the statement itself is not logically contradictory. The paradox also has a dual form involving belief rather than assertion. Consider the statement, "I believe it is raining, but it is not raining." And again, this may be true. Someone can believe something false, but believing this conjunction seems irrational. Because if you believe the first conjunct, that you believe it is raining, and you also believe the second conjunct, that it is not raining, then you are aware that one of your beliefs is false, yet you continue to hold both beliefs. And this seems like a paradigm case of irrationality, holding contradictory beliefs while being fully aware of the contradiction. The more paradoxical statements reveal a kind of blindness that rational agents have about their own beliefs. You cannot rationally believe, "I believe P, but not P," even though this statement may be true, because believing it requires simultaneously believing P. Since you believe that you believe P, and beliefs about your own beliefs are generally reliable, and believing not P, which is the second conjunct, and so you end up believing both P and not P, which is a straightforward contradiction. And so the more paradoxical belief collapses into an ordinary contradiction when believed, even though it is not a contradiction when merely entertained or stated by someone else. The paradox connects to issues about self-knowledge and the transparency of belief, the idea that we have a special kind of access to our own mental states, that we know what we believe in a way that is different from how we know what others believe. And Moore's paradox suggests that this access is not merely causal or empirical, but involves a kind of rational or conceptual connection, that there are norms governing the relationship between belief and self-ascription of belief, norms that make certain combinations of beliefs irrational even when they are not logically contradictory. The paradox also appears in contexts involving other propositional attitudes. There are more paradoxical statements involving knowledge, such as P is true, but I do not know it, which seem strange to assert even though they may be true. There are billions of truths that any given person does not know, and there are versions involving desire, intention, and other mental states, each revealing similar tensions between the attitude and the self-ascription of that attitude. Some philosophers have argued that Moore's paradox reveals the limits of a purely truth-conditional semantics, the view that the meaning of a sentence is fully captured by its truth conditions, by the conditions under which it is true or false. Because more paradoxical sentences have clear truth conditions, they are true when both conjuncts are true, and yet they are assertorically defective. They cannot be rationally asserted, and this suggests that meaning involves more than truth conditions, that it includes pragmatic dimensions, norms of assertion, and the commitments that speakers undertake when they use language. Others have explored formal models of Moore's paradox using epistemic logic and doxastic logic, systems that formalize reasoning about knowledge and belief. And these formal models can represent the structure of more paradoxical statements and prove that they are not logically contradictory, while also showing why they lead to incoherence when believed or asserted. And this formal work has illuminated the structure of the paradox and connected it to other puzzles in epistemic logic, such as the knowability paradox and the surprise examination paradox. Moore's paradox remains a touchstone in philosophy of mind and language, a simple puzzle that continues to generate insights about the nature of belief, the norms of assertion, the structure of self-knowledge, and the relationship between logic and rationality. And it stands as a reminder that coherence and consistency are more complex than they first appear, that there are ways of being irrational that do not involve believing logical contradictions, that the pragmatics of language use constrain what can be rationally asserted in ways that go beyond the truth or falsity of what is said, and that the relationship between mind and world, between belief and truth, between what we think and what we say, is mediated by norms and commitments that are not fully captured by the formal apparatus of logic. And the statement sits there: it is raining. But I do not believe it is raining. True perhaps, yet absurd, unsayable, a combination of words that no rational speaker would utter. And the paradox persists, a permanent fixture in the landscape of philosophy, a puzzle that illuminates the boundaries of rational thought, the limits of self-knowledge, and the strange logic that governs the relationship between belief and assertion, between what we think and what we can coherently say about what we think. Olbers's paradox: why the night sky is dark when it should blaze with light. Look up at the night sky and you see darkness, scattered stars against a black background, empty space between the points of light. And this seems natural, seems obvious. The sky's dark because there are not many stars, because most of space is empty. But in an infinite, eternal universe filled with stars, this darkness becomes paradoxical, becomes something that should not exist. And this is Olbers' paradox, named after German astronomer Heinrich Wilhelm Olbers, who discussed it in 1823, though the puzzle was recognized earlier by others, including Johannes Kepler and Edmund Halley. And the paradox asks why the night sky is dark, when simple reasoning suggests it should be blazing bright as the surface of the sun in every direction. The argument proceeds as follows. If the universe is infinite in spatial extent and has existed forever, and if stars are distributed roughly uniformly throughout this infinite space, then every line of sight from Earth, extended far enough, must eventually intersect the surface of a star, because in an infinite universe, with infinite stars, every direction contains a star somewhere along that sight line, perhaps nearby or perhaps trillions of light years away, but somewhere, and so the entire sky should be covered with stellar surfaces, should glow with the brightness of a star, and there should be no dark spaces, no black background, only light. And yet we see darkness. We see mostly empty space with occasional bright stars. And this contradiction is Olbers' paradox. Visualize the reasoning more carefully. Imagine dividing the universe into concentric shells around Earth, like layers of an onion, each shell at a different distance, and count how many stars are in each shell. A shell at distance r has volume proportional to r squared times the shell thickness, because the surface area of a sphere grows as r squared. And if stars are uniformly distributed, then the number of stars in the shell is proportional to r squared. But the brightness of each individual star falls off as 1 over r squared due to the inverse square law of light. Light spreads out as it travels, and so the total brightness contributed by all stars in a given shell is the number of stars times the brightness per star, which is r squared times 1 over r squared. And these factors cancel, and each shell contributes the same total brightness regardless of distance. And since there are infinitely many shells in an infinite universe, the total brightness is infinite, and the sky should be infinitely bright. And even if we account for stars blocking each other, eventually every sight line intersects a star, and the sky should glow uniformly with the brightness of stellar surfaces. The resolution of Olbers' paradox involves recognizing that the universe is not infinite and eternal in the way the paradox assumes. Modern cosmology tells us that the universe has a finite age, about 13.8 billion years, and light travels at a finite speed, and so we can only see light from stars within our observable horizon, stars whose light has had time to reach us. And this limits the number of stars we can see. And more importantly, the universe is expanding, and distant stars are receding from us, and their light is redshifted, stretched to longer wavelengths and lower energies by the expansion of space. And this redshift dims distant starlight. And for sufficiently distant stars, the redshift is so extreme that their light is shifted into the infrared or radio spectrum, invisible to our eyes. And the combination of finite age and cosmological expansion means that only a finite amount of starlight reaches us, and the night sky is dark. Not because stars are sparse, but because the universe has not existed long enough for light from all stars to reach us, and because expansion dims the light from distant sources. Another factor is the finite lifetime of stars. Stars are not eternal. They form, they shine for millions or billions of years, and they die. And in a finite age universe, not all regions have had time to form stars, and not all stars have been shining throughout cosmic history, and so the background radiation from stars is further reduced. And these factors combine to ensure that the night sky is dark despite the vast number of stars in the universe. The paradox also touches on thermodynamics and equilibrium, because if the universe were infinite, eternal, and static, with stars distributed uniformly, then eventually the radiation from all these stars would fill space uniformly. Space would reach thermal equilibrium with stellar surfaces, and everything would be at the same temperature as the surface of a star, about 6,000 degrees Kelvin, and Earth would be vaporized, life would be impossible, and the darkness of the night sky is evidence that the universe is not in thermal equilibrium, is not static and eternal, but is instead dynamic, expanding, and young. Olbers's paradox played a role in the development of modern cosmology. It was one piece of evidence that the universe cannot be static and eternal, that something must be different about the large-scale structure of space and time. And when Edwin Hubble discovered in the 1920s that the universe is expanding, that distant galaxies are receding from us, this provided a natural resolution to Olber's paradox. The expansion redshifts and dims distant light, preventing the accumulation of infinite brightness, and the finite age of the universe, confirmed by observations of the cosmic microwave background and the distribution of galaxies, completes the resolution, ensuring that we see only a finite amount of cosmic history, only the light from stars within our past light cone. The paradox also has poetic resonance. It asks why there is darkness, why night exists, why space is not filled with light. And the answer is that darkness is a consequence of time and change, of the universe having a beginning, of stars being born and dying, of space expanding and carrying light away. And darkness becomes not an absence, but a presence, not a void, but a canvas. Evidence of cosmic history, evidence of the dynamic evolving universe we inhabit. And the dark night sky, far from being empty or boring, is rich with information. Tells us about the finite age of the cosmos, about the expansion of space, about the distribution and evolution of stars and galaxies. And Olber's paradox, resolved but not forgotten, remains a reminder that even simple observations, like the darkness of night, can contain profound mysteries, can require deep theories to explain, and can reveal fundamental truths about the nature of the universe. The stars shine against the darkness, scattered lights in an empty sky, and the darkness itself is meaningful, is informative, is the signature of a finite age expanding universe. And Olber's paradox, resolved by modern cosmology, endures as a teaching tool, as an illustration of how seemingly simple questions can have complex answers, and as a monument to the human capacity to wonder about the ordinary, to see puzzles where others see only the familiar, and to pursue those puzzles until the universe reveals its secrets. Libet's experiments. Paradox: why your brain decides before you do. A neuroscientist named Benjamin Libet designs an experiment to investigate the timing of conscious decision-making, to discover when conscious intention arises relative to brain activity and action. And subjects sit before a screen with a moving dot like a clock hand, and they are instructed to flex their wrist whenever they feel like it, spontaneously, without planning in advance. And while they watch the screen, they note the position of the dot when they first become aware of the intention to move, when they first consciously decide to flex. And meanwhile, electrodes measure brain activity, specifically measure the readiness potential, a build-up of neural activity that precedes voluntary movements. And Libet's finding is striking and controversial. The readiness potential begins several hundred milliseconds before the subject reports conscious awareness of the intention to move. The brain activity precedes conscious intention by about 300 to 500 milliseconds. And this seems to show that the brain decides to move before consciousness decides. That unconscious neural processes initiate the action, and conscious intention is a kind of afterthought, an epiphenomenon, something that arises after the decision has already been made at the unconscious level. And this finding appears to challenge free will, appears to show that conscious decisions do not cause actions but merely accompany them or follow them. And this is Libet's experiment's paradox, the discovery that our conscious intentions come too late to cause our actions, come after the brain has already committed to acting. And this creates philosophical puzzles about the nature of volition, about whether we truly initiate our actions or merely become aware of them after unconscious processes have already set them in motion. Imagine the subject in Libet's experiment, watching the dot move around the screen, waiting for the urge to flex their wrist, and suddenly they feel the intention, They become aware of wanting to move, they experience the conscious decision, and they note the position of the dot. And a moment later, their wrist flexes, and this sequence feels like the intention caused the movement. Feels like they decided consciously and then acted. But the brain recordings tell a different story. Show that neural activity associated with the movement began several hundred milliseconds before the conscious intention that the brain was preparing to move, before consciousness knew about it. And this temporal order suggests that consciousness does not initiate action, but only monitors it, only becomes aware of decisions that have already been made unconsciously. And if this is correct, then conscious free will is an illusion, is a feeling that arises after the fact, after unconscious processes have already determined what will happen. The paradox is that subjectively, we feel like we consciously decide and then act, feel like conscious intention is the cause of action, but objectively, the neural evidence suggests that unconscious processes cause both the action and the conscious intention, that consciousness is not in the driver's seat but is a passenger, observing but not controlling, and this disconnect between subjective experience and objective reality creates the paradox, makes us wonder whether free will is real or illusory, whether we are agents who initiate actions or spectators who witness actions that our brains have already decided to perform. Visualize the timeline. At time 0, the readiness potential begins. Unconscious neural activity starts building up. At time 300 milliseconds, the subject becomes consciously aware of the intention to move. At time 500 milliseconds, the movement occurs. And the critical question is what causes what? Does the conscious intention at 300 milliseconds cause the movement at 500? Or does the unconscious readiness potential at time 0 cause both the conscious intention and the movement? And Libet's data suggests the latter, suggests that unconscious brain activity is the real cause, is the initiator, and conscious intention is just another effect, another consequence of the unconscious process. And if this is right, then conscious will is causally inert, does not actually produce behavior, is epiphenomenal. Many philosophers and scientists have challenged Libet's interpretation. One response questions the measurement of conscious intention, argues that asking subjects to note when they became aware of intending is asking them to introspect a process that might not be accessible to introspection, and the reported time of intention might be inaccurate, might be systematically delayed, and subjects might become aware of intending earlier than they report, perhaps at the same time as the readiness potential begins. And if conscious awareness actually coincides with the readiness potential, then there is no paradox. Consciousness is part of the initiating process, not an afterthought. Another response distinguishes between different kinds of decisions, argues that Libet's experiments involve arbitrary decisions, spontaneous movements without specific goals or reasons, and these are not typical of the kinds of decisions we care about when discussing free will. And meaningful choices, choices based on deliberation and reasons, might involve different neural processes, might involve consciousness more centrally. And Libet's findings about arbitrary wrist flexions do not generalize to all decisions, do not show that conscious deliberation is always epiphenomenal, and free will might be preserved for rational choices even if spontaneous impulses are unconsciously initiated. A third response questions the interpretation of the readiness potential, argues that early neural activity does not necessarily represent a decision or commitment to act, but might represent preparation, might be part of the process of forming an intention rather than being the cause of intention, and consciousness might be involved throughout this process. And the readiness potential and conscious intention might be parts of a single, integrated process rather than separate causes. And Libet's interpretation assumes too sharp a separation between unconscious and conscious processes, treats them as competing causes when they might be cooperative aspects of a single decision-making system. Some philosophers embrace Libet's findings, argue that they confirm what we should have known all along, that consciousness does not have magical causal powers, that all mental processes are brain processes, and brain processes are physical processes that operate according to causal laws, and conscious states are aspects of brain states, not separate entities that somehow reach into the physical world to cause behavior. And Libet's experiments help dispel the Cartesian illusion that consciousness is a separate substance with independent causal power, help show that we are physical beings whose actions are caused by physical brain processes, and consciousness is part of this physical system, not a separate controller. Libet himself proposed that consciousness might not initiate actions, but might have a veto power, might be able to stop actions that unconscious processes have initiated, and he found some evidence for this, found that conscious intention could inhibit movements, even after the readiness potential had begun, and this veto function preserves a role for conscious will, makes consciousness a gatekeeper if not an initiator, and this preserves some form of free will, free won't rather than free will, the ability to consciously inhibit unconsciously initiated impulses. The experiments have been repeated and refined by many researchers with various results, some confirming Libet's findings and others qualifying them, showing that the relationship between brain activity, conscious awareness, and action is more complex than Libet's original interpretation suggested, and the debate continues with no consensus about what the experiments show about free will, about whether they undermine it or are compatible with it. And the paradox persists as a live issue in neuroscience and philosophy. The subject flexes their wrist, notes the time of intention, and the electrodes record the readiness potential, and the timing reveals that brain activity preceded awareness. And the question remains what this means for free will, whether it shows that consciousness is epiphenomenal, that we do not truly initiate our actions, or whether the interpretation is wrong, whether consciousness is involved earlier than subjects report, or whether the experiments test the wrong kinds of decisions. And Libet's paradox endures as one of the most discussed and controversial findings in the neuroscience of volition, a set of experiments that appears to show that free will is an illusion, that our conscious sense of agency is a feeling that arises after decisions have already been made, and whether this appearance is accurate, whether the paradox is real or illusory, remains one of the most important questions at the intersection of neuroscience and philosophy. And the readiness potential builds, and consciousness awakens, and action follows, and the temporal order creates the paradox, and the debate continues. Epimenides' paradox. A poet from Crete named Epimenides once declared that all Cretans are liars, and this statement, simple as it seems, has echoed through the centuries as one of the earliest recorded paradoxes, a puzzle that predates even the formal study of logic, and yet contains within it the seeds of contradictions that still trouble philosophers today. If Epimenides himself is a Cretan and he claims that all Cretans are liars, then his statement must be a lie. But if his statement is a lie, then not all Cretans are liars, which means some Cretans tell the truth, which could include Epimenides himself, which means his statement might be true after all, which means all Cretans are liars, which means his statement is a lie and the cycle begins again. The paradox is not quite as airtight as the liar paradox that would emerge later, because calling someone a liar does not mean they always lie, only that they lie sometimes. And so there remains a sliver of logical escape, a possibility that Epimenides is telling the truth on this one occasion while still being a liar in general, or that his statement is partially true and partially false, depending on how it is interpreted. St. Paul referenced the paradox in his letter to Titus, quoting Epimenides and adding that the statement is true, seemingly unaware or unconcerned with the logical contradiction embedded in his endorsement. And this has led to centuries of theological and philosophical debate about what Paul intended and whether Scripture itself contains a paradox. The ancient Greeks recognized the puzzle, but lacked the formal tools to fully analyze it, treating it more as a rhetorical curiosity than a serious threat to logic. And it was not until the development of modern symbolic logic that the deeper implications became clear. The paradox belongs to a family of self-referential statements that collapse under their own weight, and Bertrand Russell would later use variations of this structure to reveal cracks in the foundation of mathematics, proving that not all sets can be safely defined, that not all statements can be assigned a truth value without contradiction. Some philosophers argue that the Epimenides paradox is weaker than its descendants because it depends on empirical facts about Cretans rather than purely logical structure, and that if we simply reject the premise that all Cretans are liars, the paradox dissolves, unlike the pure liar paradox which creates contradiction through its form alone. Others see it as an early recognition that language can turn against itself, that statements about truth and falsehood require careful handling, that self-reference introduces dangers that must be acknowledged and navigated. The paradox also raises questions about identity and generalization, about what it means to make sweeping claims about groups of people, and whether such claims can ever be fully coherent when the speaker is part of the group being described. Epimenides stands at the origin of a long tradition of logical puzzles, his words reverberating through time. A poet who may not have fully understood what he had unleashed, but who nevertheless gave voice to one of the fundamental tensions in human thought, the way that truth can fold back on itself and become strange, unstable, uncertain. Laplace's demon, the mind that knows everything that will ever happen. A supremely intelligent being, a vast intellect that knows the position and velocity of every particle in the universe at a single instant, stands outside time and space. And this being, this demon, as Pierre-Simon Laplace called it in 1814, possesses the complete laws of physics, the equations that govern how particles interact and move, and with this information, the precise state of every atom and the exact rules of motion. The demon can calculate the future, can determine with perfect accuracy where every particle will be at any future time, can predict every event, every thought, every decision, every outcome, from the fall of a raindrop to the rise of civilizations, from the collision of atoms to the death of stars. And in principle, the demon could also calculate the past, could trace every particle's trajectory backward to determine exactly how the present arose from previous states. And so this demon, given sufficient computational power, could know everything that has happened and everything that will happen. The entire history of the universe, past and future, encoded in a single snapshot of the present. And this is Laplace's demon, a thought experiment about determinism, about whether the universe is a clockwork mechanism, where the future is entirely determined by the past, where free will is an illusion, where everything that will ever happen is already decided, already implicit in the current state of things. Imagine the demon's knowledge as a vast table, infinitely long, listing the position and velocity of every particle, every electron, every quark, every photon, trillions upon trillions upon trillions of entries, and the demon has access to all this information perfectly, knows it exactly, with infinite precision. And the demon also knows Newton's laws, or perhaps Einstein's field equations, or quantum mechanics, knows the rules that govern how these particles influence each other, how forces propagate, how energy transfers, and with this knowledge, the demon can simulate the universe, can run the equations forward in time, calculating step by step how the particles will move, how they will collide and interact, and the simulation produces a prediction, a complete specification of the universe at every future moment. And this prediction, if the laws of physics are deterministic, is not probabilistic but certain. The future is determined, fixed, inevitable, and the demon knows it all. The implications are profound and troubling, because if Laplace's demon is possible, If the universe is deterministic, then free will becomes problematic, becomes perhaps an illusion, because every decision you make, every thought you have, every action you take is the result of particles in your brain following physical laws, and those particles are moving according to rules determined by their initial conditions, and those initial conditions were set by earlier states, going back to the beginning of the universe. And so your choices are not free but predetermined, decided billions of years ago when the universe began, and you are not an agent but an automaton, a complex machine that operates according to fixed rules, and the feeling of making choices, of deliberating and deciding, is a subjective experience produced by computational processes in your brain. But the outcome was never in doubt, was determined from the start, and this conclusion undermines moral responsibility, undermines the concepts of praise and blame, undermines the notion that people could have done otherwise, and it raises the question of what it means to be human if our actions are all predetermined. But Laplace's demon faces several obstacles, several reasons why even in principle it might be impossible. The first obstacle is quantum mechanics, which was unknown in Laplace's time, but is now recognized as fundamental to physics, and quantum mechanics is probabilistic, not deterministic. The Heisenberg uncertainty principle states that we cannot know both the position and velocity of a particle with perfect precision. There is an irreducible indeterminacy, a fundamental limit on what can be known, and when we measure a quantum system, the outcome is random, governed by probabilities but not determined. And so Laplace's demon cannot have the precise initial conditions it needs, cannot know the exact state of the universe, and even if it could, the laws of quantum mechanics only predict probabilities for future events, not certainties, and so the future is genuinely open, not determined, and Laplace's demon is impossible. The second obstacle is chaos sensitivity to initial conditions, where tiny unmeasurable differences in starting states lead to vastly different outcomes over time. Weather systems, planetary orbits, fluid flows, all exhibit chaotic behavior, where prediction becomes impossible beyond a certain time horizon, because errors in measurement, no matter how small, grow exponentially and eventually dominate. And even if quantum mechanics were not an issue, even in a classical deterministic universe, practical prediction would be impossible for chaotic systems, and the demon would need infinite precision, infinitely accurate knowledge of initial conditions, and any finite approximation, no matter how good, would fail after sufficient time. And so the demon's predictions would be useless for complex systems on long time scales. The third obstacle is computational. Even if the demon had perfect information and deterministic laws, simulating the universe requires computing power, requires processing the interactions of every particle, and the universe contains roughly 10 to the 80 particles, and computing their evolution requires resources, and some physicists have argued that simulating the universe would require a computer as large as the universe itself, and such a computer could not run faster than the universe it simulates, could not predict the future faster than the future unfolds. And so the demon could not tell you tomorrow's events before tomorrow arrives, and the demon becomes useless as a predictor, reduced to a mere recorder that reconstructs what has already happened rather than foretelling what will happen. Visualize the universe as a vast machine, gears turning, particles moving, and Laplace's demon standing outside, watching the machine, knowing the position of every gear, the velocity of every component, and calculating how the machine will continue to turn. But the demon is blocked by quantum uncertainty, cannot measure the gears precisely enough, is blocked by chaos, cannot maintain accuracy over time, is blocked by computational limits, cannot perform the calculation fast enough, and so the demon, mighty as it seems, is impossible. The universe resists total prediction, resists complete knowledge, not because of practical limitations, but because of fundamental features of physical law and determinism. Even if it were true, does not grant us the power to predict, and the demon remains a thought experiment, a symbol of a kind of knowledge that cannot exist, a vision of omniscience that is ruled out by the nature of reality itself. Laplace's demon also raises philosophical questions about explanation and understanding, because even if we cannot predict the future, even if determinism fails or the demon is impossible, we still seek to explain why things happen, to trace causes and effects, to understand the mechanisms that generate events. And this explanatory project does not require Laplacian determinism, does not require perfect prediction, but only patterns, regularities, laws that hold approximately, and science proceeds without the demon, without omniscience, by finding partial explanations, probabilistic models, statistical regularities, and these are sufficient for understanding, for technology, for navigating the world. And the demon's impossibility does not doom science but liberates it, frees it from the burden of total prediction, allows it to focus on what can be known rather than lamenting what cannot. The demon sits in conceptual space, all-knowing and impotent, knowing everything but unable to act, unable to exist, blocked by uncertainty, by chaos, by computation, and Laplace's vision of a deterministic clockwork universe fades, replaced by a more subtle picture, a universe governed by laws but not wholly determined, open to chance, to randomness, to emergence, where the future is not written in the present but unfolds through processes that are partly lawful and partly random, and free will, though not proven, is at least not obviously refuted, and moral responsibility, though challenged, survives because even if determinism were true, even if all actions are caused by prior states, we still distinguish between actions that flow from deliberation and those that do not, between agents who respond to reasons and those who do not, and these distinctions matter, ground our practices of praise and blame, and Laplace's demon, impossible and paradoxical, remains a touchstone in debates about determinism, free will, and the limits of knowledge, a thought experiment that has shaped centuries of discussion and continues to challenge our understanding of what it means to predict, to know, and to be free. Maxwell's demon, the tiny creature that could break the universe. Imagine a box divided into two halves by a partition. The partition has a small door, operated by a tiny intelligent being, a demon as physicist James Clerk Maxwell called it in 1867, and the box contains gas molecules bouncing around randomly, some moving fast and some moving slow. Hot molecules and cold molecules mix together, and the demon, perched at the door, watches the molecules approach and makes decisions. When a fast-moving hot molecule approaches from the left, the demon opens the door and lets it pass to the right. And when a slow-moving cold molecule approaches from the right, the demon opens the door and lets it pass to the left. And when molecules moving in the wrong directions approach, the demon keeps the door closed. And over time, this sorting process concentrates hot molecules on the right side and cold molecules on the left side, creating a temperature difference without any energy input, just the demon's intelligence and careful timing. And once a temperature difference exists, it could be used to run a heat engine, to extract work, to power machines. And this seems to create energy from nothing, seems to violate the second law of thermodynamics, which states that entropy always increases, that heat flows from hot to cold, and never the reverse without work being done. And so, Maxwell's demon presents a paradox, a thought experiment, where intelligence appears to defeat fundamental physical law, where information and cleverness seem to allow perpetual motion. And this puzzle troubled physicists for over a century, until the resolution emerged from understanding the relationship between information and thermodynamics. Visualize the demon at work, watching molecules approach, each molecule carrying kinetic energy, moving at some velocity determined by temperature. And the demon perceives each molecule, measures its speed, decides whether to open or close the door, and executes the decision perfectly. and after many such operations, the gas on the right is hotter than the gas on the left. Entropy has decreased in the gas. Order has emerged from disorder, and this seems impossible because the second law of thermodynamics is supposed to be universal, supposed to apply to all closed systems, and the box with the demon should be a closed system. No energy enters or leaves, and yet entropy decreases, and if entropy can decrease, then the second law is violated, and if the second law can be violated, then all of thermodynamics collapses. Heat engines could run at impossible efficiencies, refrigerators could cool without power input, the universe's arrow of time could reverse, and physics as we know it breaks down. The resolution emerged gradually through the work of several physicists, including Leo Szilard, Leon Brillouin, and Charles Bennett, and the key insight is that the demon must gather information about the molecules, must measure their velocities, must store this information in memory, and these operations have thermodynamic costs. The demon's brain or computer or measuring device must interact with the molecules to measure them, and this interaction dissipates energy, and more importantly, the demon's memory fills up with information about past measurements, and eventually the memory must be erased to make room for new measurements. And Rolf Landauer proved in 1961 that erasing information has a fundamental minimum thermodynamic cost. Erasing one bit of information requires dissipating at least a certain amount of heat proportional to temperature. And this heat generation increases the entropy of the environment. And when the entropy increase from information erasure is included in the accounting, the total entropy of the system plus demon never decreases. The second law is preserved. The demon cannot create a perpetual motion machine because the cost of gathering and erasing information exactly compensates for the entropy decrease in the gas. Imagine the demon's memory as a tape with bits that record whether each molecule was fast or slow, and as the demon sorts molecules, the tape fills up. 0 for slow molecule, 1 for fast molecule, and the tape grows longer and longer, and eventually the demon runs out of memory space and must erase the tape to continue operating. And the erasure process, Landauer showed, must dump heat into the environment, must increase entropy elsewhere. And the entropy increase from erasure is at least as large as the entropy decrease from sorting, and so the net change in entropy is 0 or positive, never negative. And the second law holds: the demon cannot beat thermodynamics. Intelligence and information do not provide a loophole. They are themselves subject to thermodynamic constraints. And information is physical, has energy costs, has entropy, and cannot be manipulated freely without thermodynamic consequences. The paradox and its resolution have profound implications for computer science, for the theory of computation, for the relationship between information and physics. Because Landauer's principle establishes that computation has fundamental physical limits, that there is a minimum energy cost for irreversible operations like erasing bits, and this cost sets a lower bound on the energy consumption of any computer. And it explains why computers generate heat, why data centers require enormous cooling systems, why information processing is not free, and it unifies information theory and thermodynamics, showing that bits and entropy are connected, that forgetting information has thermodynamic consequences, that memory erasure increases disorder in the universe. Maxwell's demon also appears in discussions of the arrow of time, the question of why time flows forward, why we remember the past but not the future, why causes precede effects. And the second law of thermodynamics provides an answer: entropy increases, and this increase defines a direction for time. And if Maxwell's demon could violate the second law, then the arrow of time could reverse, the past and future could become symmetric, and the resolution of the demon paradox reinforces the second law, confirms that entropy really does always increase when all systems, including observers and their memories, are accounted for. And this grounds the arrow of time in fundamental physics, connects our subjective experience of time's flow to objective thermodynamic processes. The demon has also inspired practical research into nanoscale systems and molecular machines, because modern technology approaches the scale where Maxwell's demon scenarios become relevant, where individual molecules can be manipulated, where quantum effects and thermal fluctuations dominate, and researchers have built experimental realizations of Maxwell's demon using feedback control, using sensors and actuators to sort particles or extract work from thermal fluctuations. And these experiments confirm Landauer's principle, confirm that information processing has thermodynamic costs, and they explore the limits of miniaturization, the minimum size and energy consumption of computers, and the ultimate efficiency of engines and refrigerators. The tiny demon sits at the door, watching molecules, sorting them, concentrating energy, and for a moment it seems to defeat the second law, seems to create order from chaos. But the illusion fades when the full system is considered, when the demon's memory and the information it gathers are included, when the cost of erasure is accounted for, and the second law stands, unbroken, universal, and the demon, far from being a threat to thermodynamics, becomes a tool for understanding it. A thought experiment that revealed deep connections between information and entropy, between computation and physics, between what we know and what we can do, and Maxwell's demon endures, not as a paradox, but as a solved problem with profound implications, a puzzle that took over a century to fully resolve, and a reminder that even the most abstract thought experiments can illuminate fundamental truths about the physical world, about the nature of information, about the limits of what is possible, and about the deep unity between different branches of physics, between thermodynamics and information theory, between entropy and knowledge. And the demon remains, a fixture in physics pedagogy, a symbol of the power of thought experiments, and a monument to the principle that information is physical, that knowledge has costs, and that nothing, not even intelligence, escapes the iron laws of thermodynamics. Moore's open question. Argument why good cannot be defined. A philosopher claims to have defined goodness, claims that good means pleasure, or good means what evolution favoured, or good means what most people approve of, and the definition is offered with confidence, with arguments and evidence supporting it, and yet G.E. Moore, in his 1903 book Principia Ethica, pointed out a fatal problem with all such definitions, a problem so simple and devastating that it has shaped ethics ever since. And the problem is this: take any proposed definition of good, any equation of goodness, with some natural property, and you can always ask a meaningful question. You can ask, but is that property itself good? And the fact that this question remains open, remains intelligible, and not obviously silly, shows that the definition has failed, shows that good has not been captured by the natural property. And this is Moore's open question argument, a challenge to naturalistic definitions of good that attempts to prove that goodness is indefinable, that it cannot be reduced to any natural fact or property, that it is a simple, unanalyzable concept that we grasp directly through moral intuition but cannot explain in other terms. Imagine someone says good means pleasant, pleasure is what good is, and now Moore asks the open question, but is pleasure good? And this question makes sense, is not absurd, is not like asking whether bachelors are unmarried men, where the question is trivially answered by the definition. And the fact that we can meaningfully ask whether pleasure is good shows that good does not mean the same thing as pleasant. Otherwise, the question would be equivalent to asking whether pleasant things are pleasant, which is a meaningless tautology. And since the question is not meaningless, since we can intelligently disagree about whether pleasure is good, the definition must be wrong, must have failed to capture what goodness really is. The same argument applies to any naturalistic definition. If someone says good means evolutionarily advantageous, we can ask, but is what evolution favoured good? And this is an open question. Many people would say no, that evolution produces traits that help survival and reproduction, but not necessarily traits that are morally good. That rape and infanticide might be evolutionarily advantageous in some contexts, but are not good, and so the definition fails. Or if someone says good means desired by most people, we can ask, but is what most people desire good? And again, this is open. We can imagine societies where most people desire things that are actually bad, where popular opinion is mistaken, and so the definition fails again. More concluded that good is indefinable, not because we do not know what it is, but because it is a simple, primitive concept, like yellow or existence, something that cannot be broken down into simpler parts or explained in other terms, but must be grasped directly. And we know good through moral intuition, through a kind of perception that is not sensory but intellectual. And different people's intuitions might disagree, but that does not mean goodness is subjective. It might mean that some people perceive moral reality more clearly than others, just as some people have better colour vision, and Moore's position is a form of non-naturalism, the view that moral properties are real but not natural, not part of the physical world studied by science, but a distinct realm of normative facts that exist objectively. The open question argument has generated enormous controversy. Critics argue that it proves too much, that the same reasoning would show that nothing can be defined, because for any definition, we can ask an open question. If water is H2O, we can ask, but is H2O water? And before we learned the chemistry, this question was open. People could meaningfully disagree, and yet we now accept that water is H2O as a correct identity. Not a definition of meaning, but an empirical discovery about what water turns out to be. And perhaps good is like this. Perhaps good is identical to some natural property, not as a matter of meaning, but as an empirical fact about what goodness turns out to be. And the open question shows only that we have not yet discovered which natural property good is, not that no such property exists. Others argue that the open question argument assumes too much about how meaning works, assumes that if two terms mean the same thing, then they must be obviously synonymous. But this is false. Morning star and evening star both refer to Venus, but it was not obvious. People could meaningfully ask whether the morning star is the evening star. And so Moore's test fails. The fact that a question is open does not prove that the terms do not refer to the same thing, and so the open question argument does not establish that good is indefinable, only that the definition is not obvious, not transparent. And this leaves room for naturalistic theories that identify goodness with some natural property as an empirical discovery rather than a conceptual analysis. Visualize Moore's argument as a test applied to proposed definitions. Each definition is presented, good equals X, and Moore applies the test. He asks, is X good? And if the question is intelligible, if it makes sense to ask, if competent speakers can understand the question and disagree about the answer, then the definition fails. X does not capture what good means, and Moore applies this test to definition after definition. Hedonism says good equals pleasure. Moore asks, is pleasure good? The question makes sense. Test failed. Naturalism says good equals natural property. Why? Moore asks, is why good? The question makes sense. Test failed. And the test seems to show that no natural property can be identical to goodness. That good resists reduction, resists naturalization, stands apart from the world of facts, and refers to something normative, something that cannot be captured by descriptive language. The argument has implications for metaethics, for the question of what kind of thing goodness is. If Moore is right, then moral realism, the view that moral facts exist objectively, must be non-naturalist, must accept that moral properties are sui generis, distinct from natural properties, irreducible to physics or biology or psychology. And this raises questions about how we can know moral facts, how moral properties relate to natural properties, whether moral facts can cause anything or play any role in explaining behaviour. And non-naturalism faces challenges, struggles to explain how we perceive non-natural properties, how they fit into a scientific worldview, whether they're compatible with naturalism about everything else. The open question argument also influenced emotivism and expressivism, non-cognitivist views that deny moral statements are factual claims at all, argue instead that moral language expresses attitudes or emotions rather than describing reality, and these views claim to explain why the open question is always open, because good does not refer to any property, natural or non-natural, but expresses approval or prescribes action. And so asking whether X is good is asking whether to approve of X, whether to pursue it. And this is always an open question, always something we can meaningfully deliberate about. But the non-cognitivists deny Moore's conclusion, deny that goodness is a real property we intuit, argue instead that moral language has a different function, is not in the business of describing reality, but of expressing commitments and guiding action. Moore's argument changed the landscape of ethics, forced philosophers to take seriously the question of whether moral properties are natural or non-natural, whether moral knowledge is empirical or a priori, whether ethics can be reduced to science or remains a distinct domain, and the argument remains controversial. Some see it as a decisive refutation of naturalism. Others see it as a confusion about meaning and reference. And the debate continues, with naturalists proposing sophisticated identities between moral and natural properties, with non-naturalists defending irreducible normativity, and with non-cognitivists denying that moral language describes properties at all. And Moore's open question sits at the centre of these disputes, a simple test that reveals deep issues about meaning, about value, about the relationship between facts and norms, and about whether goodness is something we discover in the world or something we project onto it. And the question remains open, always open, because that is what good does. It resists definition, resists reduction, remains stubbornly normative, always inviting the question, but is that really good? And no answer closes the question, no definition settles it. And Moore's argument endures as a reminder that ethics is not reducible to any other domain, that the normative cannot be fully naturalized, and that goodness, whatever it is, stands apart, indefinable, and irreducible, a primitive concept that we use but cannot explain. Goodman's grue paradox. When emeralds turn blue at midnight, a philosopher invents a new color term, grue, and grue is defined as follows. An object is grue if it is observed before time t and is green, or if it is not observed before time t and is blue, where t is some future date, perhaps January 1st of next year. And this definition is strange, is artificial, combines observation and time in a way that ordinary colour terms do not. But the definition is precise, is perfectly clear. And now the philosopher considers emeralds and notes that all emeralds observed so far have been green. And these observations support the hypothesis all emeralds are green. And the same observations also support the hypothesis all emeralds are grue because all observed emeralds satisfy both descriptions. They are green, which means they are grue up to time t, and both hypotheses are equally well supported by the evidence. Both fit all observations perfectly, and yet the two hypotheses make different predictions about the future. The first predicts that emeralds examined after time t will be green. The second predicts they will be blue. And so we have two hypotheses, equally supported by evidence, making opposite predictions. And the question is, which hypothesis should we believe? Which generalization should we project into the future? And Nelson Goodman poses this as a problem about projectability, about which predicates can legitimately be used in inductive inferences. And this is the grue paradox, also called Goodman's new riddle of induction, a puzzle that shows that not all evidence-supported hypotheses are equal, that some predicates are projectable and others are not, and the challenge is to explain what makes green projectable and GRU not, what distinguishes legitimate from illegitimate generalizations. Imagine living in a world where emeralds are GRU, where all emeralds observed before time t are green, but all emeralds examined after time t are blue. And from the perspective of someone before time t, this is indistinguishable from a world where emeralds are simply green. All observations are the same, and yet the two worlds are radically different, will diverge dramatically after time t. And the puzzle is that evidence accumulated before t does not distinguish between these possibilities, does not tell us which world we inhabit, and so induction alone cannot determine which hypothesis to accept, cannot tell us whether emeralds are green or GRU. And this reveals that induction requires more than just fitting evidence, requires principles about which predicates are projectable, which generalizations are legitimate. And these principles cannot themselves be justified inductively without circularity. Visualize the timeline with time t marking a boundary, and on one side of the boundary, all observed emeralds are green. And the question is what happens after the boundary. Do emeralds remain green, or do they become blue? And the hypothesis, all emeralds are GRU, says they switch colours. But this switching is built into the definition of GRU, is a feature of how the predicate is defined rather than a feature of emeralds themselves. And this reveals something important, that the GRU hypothesis is gerrymandered, is artificially constructed to fit past observations while making a different prediction about the future. And our intuition is that such gerrymandered hypotheses should not be projected, should not be taken seriously, but explaining why requires articulating a principle that distinguishes natural from gerrymandered predicates. Goodman's own solution appeals to entrenchment, argues that green is projectable because it has been used successfully in many past inductions, has become entrenched in our language and our theories, while GRU is a newcomer, is defined artificially, has no history of successful projection, and so we should prefer green over GRU, not for any logical reason, but for pragmatic reasons, because green has proven its worth. And this solution ties projectability to linguistic and scientific practice, makes it a matter of history rather than logic. And some find this unsatisfying, find it too relativistic. But Goodman argues that there is no deeper justification available, that entrenchment is as good as justification gets for inductive inference. Another response argues that GRU is not a genuine predicate, is not natural, because it is defined in terms of observation and time, includes reference to specific moments and observers, and genuine properties should be observer-independent, should not change based on when or whether they are observed. And green is natural in this sense, refers to a real property that objects have regardless of observation, while GRU is artificial, is defined through disjunction and reference to observation, and so only natural predicates are projectable. And this solution requires explaining what makes a predicate natural, what distinguishes genuine properties from artificial constructions. And this leads to metaphysical questions about the nature of properties, about whether naturalness is objective or conventional. A third response from a Bayesian perspective argues that GRU hypotheses are less probable than green hypotheses given reasonable priors, because GRU hypotheses postulate discontinuities, postulate that properties change suddenly at arbitrary times, and such discontinuities require explanation, require reasons, and in the absence of such reasons we should assign low prior probability to GRU hypotheses. And so while GRU fits the evidence as well as green, GRU is less probable overall because of its lower prior, and this solution appeals to simplicity and parsimony, treats continuous properties as more probable than discontinuous ones, and explains projectability in terms of prior probabilities rather than entrenchment or naturalness. The GRU paradox also reveals that the problem of induction is deeper than Hume recognized, because Hume worried about justifying any inductive inference, about showing that the future will resemble the past, but even if we accept induction, we face Goodman's problem. We must choose which respects the future, will resemble the past, must decide which predicates to project, and different choices lead to different predictions. And there is no algorithm, no mechanical procedure that tells us which predicates are projectable, which generalizations are legitimate. And so induction requires judgment, requires background knowledge, requires engagement with the actual practice of science rather than pure logical analysis. The paradox extends beyond emeralds and colours to any inductive inference, to all attempts to generalize from observed to unobserved cases, because for any pattern we observe, for any regularity we find, there are infinite GRU-like predicates that fit the pattern up to now, but diverge in the future, and choosing between these predicates cannot be done on evidential grounds alone, requires additional principles, requires distinguishing projectable from non-projectable predicates. And every scientific theory makes such choices, implicitly assumes that certain predicates are natural and others artificial. And Goodman's paradox makes these assumptions explicit, forces recognition that induction is not just about fitting evidence, but about choosing the right vocabulary, the right predicates, the right way of carving up the world. The clock approaches time T, and emeralds remain green, as they always have been, and the GRU hypothesis is refuted, is shown to have been wrong. But before time T, the evidence supported GRU as much as green, and this shows that evidence alone was insufficient, that something beyond evidence guided our preference for green, our confidence that emeralds would remain green rather than turning blue, and that something is what Goodman's paradox investigates, what it challenges, used to articulate, and the paradox remains not fully resolved, not answered by any single theory that satisfies everyone, but persistent as a challenge to theories of induction, a test case for accounts of scientific reasoning, and a reminder that generalizing from experience requires more than logic, requires substantive assumptions about the world, about which properties are real and which are artificial, about which patterns will continue and which will break. And these assumptions cannot be justified inductively without circularity, cannot be proven logically without begging the question. And so induction rests ultimately on judgment, on practices that have proven successful, on entrenchment or naturalness or simplicity. And Goodman's GRU paradox reveals this foundation, exposes the principles we rely on but cannot fully justify. And the paradox endures as one of the most important problems in philosophy of science. Hilbert's hotel paradox. A hotel with infinitely many rooms, each numbered with a positive integer, 1, 2, 3, and so on without end, stands fully occupied. Every room contains a guest, and yet when a new guest arrives, the manager is not concerned, does not turn them away, because infinity accommodates addition in ways that finite quantities cannot. And the manager simply asks each current guest to move to the next room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3, and so on, each guest shifting one room higher. And this process, applied simultaneously to all guests, leaves room 1 vacant, and the new arrival is accommodated without displacing anyone permanently. And this is Hilbert's hotel, a thought experiment devised by the mathematician David Hilbert to illustrate the counterintuitive properties of infinite sets, to show that infinite collections behave in ways that violate ordinary intuition, that they can be put in one-to-one correspondence with proper subsets of themselves, that adding elements or removing elements does not change their cardinality, and that the whole is not always greater than the part when dealing with infinity. The paradox deepens when an infinite number of new guests arrive, an infinite bus pulling up to the hotel, each passenger needing a room. And again, the manager is unperturbed, because there is a strategy to accommodate everyone. The manager asks each current guest in room N to move to room 2N. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6, and so on. And this process places all the original guests in the even-numbered rooms, leaving all the odd-numbered rooms vacant. And since there are infinitely many odd-numbered rooms, one for each positive integer, there is exactly enough space for the infinitely many new arrivals who are assigned to rooms 1, 3, 5, and so on. And the hotel, despite being full, has accommodated an infinite number of additional guests without anyone being displaced. The paradox reveals that infinite sets have a property called countable infinity. They can be placed in one-to-one correspondence with the natural numbers, and this correspondence allows for operations that seem impossible with finite sets. A fully occupied hotel with finitely many rooms cannot accommodate additional guests without evicting someone. But a fully occupied hotel with infinitely many rooms can accommodate not just one additional guest, but infinitely many. And this does not mean the hotel was not really full before. All rooms were occupied, but rather that fullness does not prevent expansion when infinity is involved, that the concepts of full and empty take on new meanings in the infinite context. Hilbert's hotel also allows for even stranger scenarios. Suppose infinitely many infinite buses arrive, each bus containing infinitely many passengers, and the hotel must accommodate all of them. And again, there is a strategy. The manager can use a pairing function, a mathematical technique that assigns a unique room number to each combination of bus number and seat number, ensuring that every passenger gets a unique room. And the hotel, starting from full occupancy, can expand to accommodate not just countably many new guests, but countably many groups of countably many new guests. Because the union of countably many countable sets is still countable, and so the total number of guests, after all the buses are accommodated, is the same cardinality as the number of guests before. Both are countably infinite. Both can be placed in one-to-one correspondence with the natural numbers. The paradox challenges intuitions about size, quantity, and comparison, because it shows that infinite sets can be proper subsets of themselves and yet have the same cardinality. The even numbers are a proper subset of all natural numbers, missing all the odd numbers, and yet there are just as many even numbers as natural numbers. Both sets are countably infinite, and this violates the Euclidean principle that the whole is greater than the part, a principle that holds for finite sets but fails for infinite sets. And this failure is not a contradiction, but a distinctive feature of infinity, a marker that distinguishes finite from infinite. Hilbert's hotel also raises questions about the physical realizability of actual infinities, because while the mathematics of infinite sets is well defined and consistent, whether actual infinite collections exist in the physical world is contested. Some philosophers and physicists argue that only potential infinities exist, processes that can continue indefinitely but never reach completion, while actual infinities, completed infinite totalities, are merely mathematical. Abstractions and the hotel paradox, with its fully occupied infinite structure, represents an actual infinity, and if such infinities cannot exist in reality, then the paradox is merely a mathematical curiosity without physical significance. But others argue that the universe may be spatially infinite, that time may extend infinitely into the past or future, and that quantum field theory involves infinite dimensional spaces. And if actual infinities are physically real, then the strange properties illustrated by Hilbert's hotel may have real-world counterparts. The hotel also appears in theological discussions about divine attributes, because an omnipotent being might be thought to perform tasks that involve manipulating infinite collections. And Hilbert's hotel shows that such manipulations are logically coherent, that infinity does not lead to contradiction, that an infinite hotel can be fully occupied and yet accommodate more guests. And this addresses worries that infinity is inherently paradoxical or incoherent, demonstrating that infinite structures follow consistent rules, even when those rules differ from finite intuitions. The hotel stands infinitely tall, infinitely long, each room numbered, each room occupied, and the new guest arrives. And there is room, always room, because infinity plus one is infinity, because infinity plus infinity is infinity, because the operations of addition and union that exhaust finite resources leave infinite resources unchanged, and the paradox reveals the strangeness of infinity, the way it defies expectation, the way it makes possible what seems impossible, and Hilbert's Hotel remains one of the most vivid and accessible illustrations of this strangeness, a story that captures in simple terms the profound weirdness of the infinite. And mathematicians use it to teach, to explain cardinality, to distinguish countable from uncountable infinities, to motivate Cantor's diagonal argument and the hierarchy of infinities. And philosophers use it to probe intuitions about existence, about the difference between actual and potential infinity, about whether the physical world contains or could contain infinite structures. And the hotel endures, a fictional place that illuminates real mathematics, a thought experiment that has become a permanent fixture in discussions of infinity, a paradox that is not a contradiction, but a revelation, a demonstration that infinity is not merely a large finite number, not merely an extension of ordinary quantity, but something qualitatively different, something that requires new concepts, new intuitions, and new ways of thinking about size, about number, about what it means for something to be more or less equal or unequal, full or empty. And the guests check in, infinitely many guests, and there is always room for more. Fichte's paradox of knowability. There is an appealing idea in philosophy, a principle that seems to capture something important about truth and knowledge, and this is the knowability principle, which states that all truths are knowable, that for any true proposition there is at least a possible situation in which someone knows that proposition, and this principle seems modest, even Platonic in spirit, suggesting that truth and knowledge are intimately connected, that reality is not fundamentally hidden or inaccessible, that the universe is intelligible in principle, even if not all truths are actually known by anyone at any given time. The principle distinguishes between what is known and what is knowable, acknowledging that many truths remain unknown, perhaps because no one has investigated them, or because the evidence is lost, or because the relevant questions have not yet been asked, but insisting that these unknown truths could be known, that there is no barrier in principle preventing them from being discovered. And this seems like a reasonable position, neither too strong like the claim that all truths are actually known, which is obviously false, nor too weak like the claim that some truths are unknowable, which seems to concede too much to skepticism and to suggest that reality contains secrets that are forever beyond our reach. But in 1963, Friedrich Fichte proved a shocking result, a theorem showing that if the knowability principle is true, then all truths are actually known, that the modest principle collapses into the absurdly strong claim it was meant to avoid. And this result, known as Fichte's paradox or the knowability paradox, has profound implications for epistemology, the philosophy of language, and debates about realism and anti-realism, and it forces philosophers to choose between giving up the knowability principle, accepting the absurd conclusion that all truths are known, or finding some way to reformulate the principle to avoid the paradox. The proof is elegant and surprisingly simple. Proceeding by reductio ad absurdum, suppose there is a truth that is unknown, call it P, and suppose also that no one knows that P is an unknown truth. That is, no one knows the conjunction P, and P is not known. And now apply the knowability principle, which says that this conjunction, being true, must be knowable, must be such that someone could know it. But here a contradiction emerges, because to know a conjunction, one must know both conjuncts. So to know P and P is not known, one must know P and also know that P is not known. But if one knows P, then P is known, which contradicts the second conjunct that P is not known, and so the conjunction P and P is not known cannot be known. It is an unknowable truth, and this contradicts the knowability principle, and therefore the assumption that there is an unknown truth must be false, and so all truths must be known. The paradox depends on the assumption that knowledge distributes over conjunction, that if you know P and Q, then you know P and you know Q, which seems uncontroversial, and on the assumption that knowledge is factive, that if you know P, then P is true, which is a standard requirement in epistemology, and so the paradox cannot be easily dismissed as relying on dubious principles. It seems to follow from our ordinary understanding of knowledge and knowability, and yet the conclusion is unacceptable. The claim that all truths are actually known is empirically false. There are obviously truths about the distant past, about the far reaches of the universe, about the inner workings of consciousness that no one knows. And so something must give, either the knowability principle or the reasoning that derives the paradox from it. One response is to reject the knowability principle, to accept that there are unknowable truths, truths that could never be known by anyone under any circumstances. And this is the position of semantic realists, who argue that truth is independent of our capacity to recognize it, that reality outstrips our epistemic abilities, that the world contains facts that are forever beyond our ken. And for realists, the knowability paradox is not a disaster, but a vindication, a proof that the anti-realist commitment to knowability is untenable, that we must accept a more robust conception of truth as radically independent of knowledge. Another response, favoured by anti-realists and verificationists, is to reformulate the knowability principle to avoid the paradox while preserving the intuition that truth and knowability are connected, and various reformulations have been proposed. Some restrict knowability to propositions that do not involve knowledge ascriptions. Avoiding the problematic, self-referential structure of P and P is not known. Others distinguish between individual and collective knowability, arguing that all truths are knowable by the epistemic community as a whole, even if not by any single individual, and still others embrace a temporal or modal reformulation, claiming that all truths could have been known at some time or in some possible world, rather than claiming that all truths are actually knowable in all circumstances. Some philosophers argue that the paradox reveals a tension in the concept of knowability itself, that knowability is not a simple modal notion, but involves complex interactions between truth, knowledge, and the conditions under which knowledge is possible, and that our intuitions about these interactions are unreliable, pulled in different directions by competing commitments, and so the paradox exposes an instability in our conceptual scheme, rather than refuting any particular philosophical position. The paradox also connects to debates about the nature of propositions and the objects of knowledge. Because the problematic conjunction P and P is not known seems strange, it is a proposition about itself in a way, a proposition whose truth depends on whether it is known, and this self-referential or quasi-self-referential structure is reminiscent of the liar paradox and other semantic paradoxes, and some responses to Fichte's paradox draw on strategies developed for dealing with those paradoxes, such as hierarchies of languages, restrictions on self-reference, or non-classical logics that reject certain principles like the law of excluded middle. The paradox has implications for constructivism in mathematics and logic, because constructivists typically endorse some version of the knowability principle, identifying truth with provability or constructibility, and Fichte's paradox threatens this identification, suggesting that even constructivists must either accept that all mathematical truths are already proved, which is absurd, or abandon the simple identification of truth with provability and develop a more nuanced account of the relationship between the two. The knowability principle, innocent as it seemed, turns out to be a Trojan horse, a seemingly modest claim that conceals a radical commitment, and Fichte's paradox forces philosophers to confront the costs of various epistemological positions, to choose between realism with its unknowable truths and anti-realism with its need to reformulate or restrict the knowability principle. And the paradox remains a central puzzle in contemporary epistemology, a test case for theories of truth and knowledge, a proof that demonstrates with crystalline clarity that even the most intuitive principles can lead to absurdity when their logical consequences are rigorously traced. And it stands as a reminder that philosophy is not merely a matter of articulating and defending intuitions, but of following arguments wherever they lead, even when they lead to conclusions that undermine the very intuitions that motivated them. And the unknown truth, the proposition that is true but not known, sits at the center of the paradox, both knowable and unknowable, possible and impossible, a conceptual anomaly that refuses to be tamed by logic or softened by reformulation. And the paradox endures, a monument to the power of formal reasoning, to reveal deep tensions in our most basic concepts, tensions that no amount of philosophical maneuvering has yet managed to resolve in a way that satisfies all intuitions and preserves all principles. And so the debate continues, philosophers proposing new solutions, new restrictions, new interpretations, and the paradox persists, waiting to trap the unwary, to challenge the confident, to remind us that even truth and knowledge, the twin pillars of epistemology, are stranger and more problematic than they first appear. Inattentional blindness. Why a gorilla walks through your vision. Unseen. A person watches a video, follows instructions to count how many times basketball players wearing white shirts pass the ball, and they count carefully, focus on the white team, track the passes, and reach a final count. And then they are asked whether they noticed anything unusual, and they say no, nothing unusual, just basketball players passing the ball. And then they watch the video again, this time without counting, and they are shocked to see that a person in a gorilla suit walked through the middle of the scene, stopped in the center, beat their chest, and walked off. And this gorilla was visible for 9 seconds, passed directly through the action, was large and obvious, and yet the person did not see it the first time, was completely unaware, was blind to the gorilla despite looking directly at it. And this is inattentional blindness, demonstrated famously by Daniel Simons and Christopher Chabray in their invisible gorilla experiment, a phenomenon showing that attention is necessary for conscious perception, that we can look directly at something and not see it if we are not attending to it. And inattentional blindness reveals that perception is not simply determined by what falls on the retina, but is determined by what receives attention. And without attention, even salient obvious stimuli can be invisible, can pass unnoticed. And this challenges the idea that we consciously perceive everything in our visual field, shows that consciousness is limited to attended stimuli, and inattentional blindness has profound implications for understanding attention, consciousness, and the limits of awareness. Imagine the experience from the inside. You're focused on counting passes, tracking the white shirts, following the ball as it moves, and your attention is fully engaged, is consumed by the counting task. And the gorilla walks through, but you do not notice it. It does not register, does not enter consciousness. And the reason is that your attention is elsewhere, is focused on the white team. And the gorilla is not relevant to the task, is not expected, is not attended to. And without attention, the gorilla remains unconscious, remains invisible, despite being visible in the sense that the image falls on your retina, that your eyes are open and pointing at it. And this distinction between seeing with the eyes and seeing with attention reveals that conscious vision requires more than physical stimulation, requires attention, requires that processing reach a certain level. And inattentional blindness shows what happens when this does not occur, shows that stimuli can be physically present but mentally absent. Inattentional blindness differs from change blindness in that it occurs even without the need for comparison, occurs for stimuli that are continuously present, not just for changes, and the phenomenon shows that attention operates not just to encode changes, but to enable any conscious perception. And when attention is fully engaged elsewhere, when there is no spare attentional capacity, even salient, unexpected stimuli are not processed to the level of consciousness. And this demonstrates that attention is a limited resource, cannot be allocated to everything simultaneously, and when fully allocated to one task, nothing else reaches awareness, and the gorilla illustrates this dramatically, is an unexpected, salient stimulus that should capture attention, that would capture attention under normal circumstances. But when attention is fully engaged in counting passes, the gorilla is filtered out, is processed pre-consciously, but does not reach awareness. Visualize attention as a gate, and stimuli must pass through the gate to reach consciousness, and the gate is narrow, allows only a limited number of stimuli through, and when the gate is occupied by task-relevant stimuli, by the white-shirted players and the ball, irrelevant stimuli like the gorilla are blocked, are filtered out, and processing of the gorilla stops at an early stage, extracts basic features, but does not construct a conscious representation, and the gorilla remains invisible. And this gating model explains inattentional blindness, explains why stimuli that are physically present can be perceptually absent, because consciousness requires passing through the attentional gate, and only attended stimuli pass through. Inattentional blindness has practical implications for understanding accidents, for recognizing that drivers can look directly at pedestrians or other vehicles and not see them if attention is focused elsewhere. And looking is not the same as seeing. Vision requires attention, and when attention is engaged with navigation or conversation or phone use, stimuli outside the focus of attention can be missed, and this contributes to accidents, to collisions that seem inexplicable because the driver was looking, had clear sight lines, but did not see, did not notice the hazard. And understanding inattentional blindness is crucial for improving road safety, for recognizing the limits of human perception, and for designing systems that account for these limits. The phenomenon also has implications for understanding consciousness, for debates about whether consciousness requires attention, whether you can be conscious of unattended stimuli, and inattentional blindness suggests that consciousness requires attention, that unattended stimuli are not conscious, are processed unconsciously, and consciousness is limited to the small set of attended stimuli. And this supports the view that consciousness is sparse, is not the rich field of awareness we subjectively experience, but is a narrow spotlight that illuminates only what attention selects. And the subjective richness is an illusion, is created by the fact that attention moves rapidly, samples different regions, and wherever it lands, detail emerges. And we confuse this serial sampling with parallel richness, assume that because detail is available everywhere, it must be present everywhere. But inattentional blindness shows this is false, shows that unattended regions are not conscious, are invisible, even when physically visible. One response to inattentional blindness argues that some stimuli do capture attention automatically, do break through even when attention is engaged elsewhere, and highly salient or biologically significant stimuli like your own name or threatening faces or sudden loud noises capture attention, override current focus, and enter awareness. And this suggests that inattentional blindness is not absolute, is not a complete gate that blocks all unattended stimuli, but is a selective filter that allows some stimuli through based on salience and relevance. And the gorilla, while salient, is not personally relevant, not threatening, not expected, and so does not capture attention, does not override the counting task. And this response preserves some role for stimulus-driven attention, while acknowledging that inattentional blindness demonstrates the dominance of goal-directed attention. Another implication concerns legal contexts, concerns eyewitness testimony, and the reliability of visual reports. Because if people can miss large obvious stimuli like gorillas when attention is engaged elsewhere, then eyewitnesses can miss critical details of crimes, can fail to notice perpetrators or weapons or actions, even when looking directly at the scene. And this challenges the assumption that eyewitnesses see everything, that memory failures are due to forgetting rather than to never encoding. And inattentional blindness shows that encoding requires attention, and attention is limited, and eyewitnesses cannot be expected to have noticed everything, and testimony must be evaluated with this in mind, must recognize the limits of attention and perception. The gorilla walks through the frame, visible and obvious, and yet unseen, unnoticed, invisible, due to inattention, due to the focus on counting passes, and the phenomenon reveals that consciousness requires attention, that seeing requires more than physical stimulation, requires cognitive engagement, requires processing resources that are limited, and when fully allocated elsewhere, nothing else reaches awareness, and the gorilla remains hidden. Hidden not by camouflage or occlusion, but by inattention, by the filter that protects consciousness from overload, that selects what matters and ignores the rest. And inattentional blindness endures as one of the most striking demonstrations in psychology, a phenomenon that challenges naive assumptions about perception, that shows the limits of awareness, that reveals consciousness as sparse and selective. And the gorilla continues to walk unseen through countless viewings, invisible to half the viewers, shocking to those who missed it. And the phenomenon persists, demonstrating that attention is the gateway to consciousness, and without attention, even gorillas are invisible. Grandi's series, when adding numbers, forever gives multiple answers. A simple mathematical series begins with 1 minus 1 plus 1 minus 1 plus 1 minus 1, continuing forever without end, alternating between adding 1 and subtracting 1. And the question emerges, what does this infinite sum equal? What value does it approach as more and more terms are added? And the paradox is that different methods of calculation give different answers, each seemingly valid, each following mathematical rules, yet reaching contradictory conclusions. And this is Grandi's series, named after the Italian mathematician Guido Grandi, who studied it in the early 18th century. And the paradox reveals fundamental questions about what it means to sum an infinite sequence, about whether all infinite series have definite values, and about the limits of algebraic manipulation when dealing with infinity. Consider the series visually. Imagine a number line where you start at 0, then move 1 unit to the right to reach 1, then move 1 unit to the left back to 0, then 1 unit right to 1 again, then 1 unit left to 0, and this pattern continues forever, oscillating between 0 and 1, never settling down, never approaching a limit in the traditional sense. And so, from this perspective, the series does not converge, does not have a sum. The partial sums bounce between 0 and 1 eternally and never stabilize. But now consider a different approach. Group the terms in pairs, taking 1 minus 1 as the first pair, which equals 0, then 1 minus 1 as the second pair, also 0, and so on. And the series becomes 0 plus 0 plus 0, continuing forever, and the sum of infinitely many zeros is 0. And so by this grouping method, the series equals 0. And this seems like a valid manipulation. Grouping terms is a standard algebraic operation, and yet it produces a definite answer where the oscillating view produced no answer. Now consider another grouping. Start by leaving the first one alone, then group all subsequent pairs, so the series becomes 1 plus the quantity negative 1 plus 1, then the quantity negative 1 plus 1, and so on. And each grouped pair equals 0. So the series becomes 1 plus 0 plus 0 plus 0, continuing forever. And this equals 1. And so by this different grouping, the series equals 1 instead of 0. And both groupings seem legitimate. Both use standard algebraic rules, yet they produce different answers, 0 and 1. And this is the heart of Grandi's paradox, that the series is sensitive to how it is manipulated, that rearranging or regrouping terms changes the result. And this suggests that the series does not have a well-defined sum in the ordinary sense. Mathematicians have developed sophisticated tools to handle divergent series, like grandies, and one approach is Cesaro summation, which assigns values to series by averaging the partial sums. And for grandie series, the partial sums are 1, 0, 1, 0, 1, 0, continuing to alternate, and the average of the first n partial sums approaches 1/2 as n grows large, because roughly half the partial sums are 1 and half are 0. And so by Cesaro summation, grandie series equals 1/2. And this method produces yet another answer, neither 0 nor 1, but the midpoint between them. And this answer has a certain aesthetic appeal. It represents the average behavior of the series, the value around which it oscillates, and it can be justified by analogy to functions. If you consider the geometric series 1 minus x plus x squared minus x cubed and so on, which converges to 1 over 1 plus x for absolute value of x less than 1, and you plug in x equals 1, you get 1 over 2. And so in some extended sense, grandie series can be said to equal 1/2. The paradox reveals that divergent series do not have sums in the way convergent series do, that assigning values to them requires making choices about what summation method to use, and different methods give different results. And there is no single correct answer, but rather a family of possible values, depending on the context and the techniques employed. And this multiplicity is not a flaw in mathematics, but a feature, a recognition that infinite sums are more subtle than finite sums, that operations that work for finite cases can break down or become ambiguous when extended to infinity. Grandie series appears in physics and engineering, in Fourier analysis, where oscillating sums arise naturally, in quantum field theory, where divergent series are regularized using techniques similar to Cesaro summation, and in signal processing, where alternating patterns must be analyzed. And in these applications, the choice of summation method is guided by physical considerations, by what gives useful predictions, by what aligns. With experimental results, and the paradox becomes less troubling, less a contradiction, and more a reminder that mathematical tools must be adapted to fit the problem, that formal manipulation must be tempered with judgment about what makes sense in context. The series also appears in philosophical discussions about infinity, about whether infinite processes can be completed, about whether the phrase, sum of infinitely many terms, has a determinate meaning or depends on conventions and choices. And Grandie's series suggests the latter, that infinity introduces ambiguities that finite mathematics avoids, that extending concepts from finite to infinite is not automatic but requires care, requires new definitions, requires acceptance, that some questions have multiple answers or no answer at all depending on how they are framed. Imagine watching someone walk back and forth on a path, taking one step forward, then one step back, then one step forward, then one step back, forever without stopping, and you are asked where they end up, and the answer is that they do not end up anywhere. They continue oscillating. But if you ask where they are on average, you might say they are halfway between the two endpoints. And if you ask where they are after an even number of steps, you say at the start. And after an odd number, you say one step forward, and none of these answers is wrong. Each captures a different aspect of the situation, and Grandie's series is similar. Different questions about the series have different answers, and the paradox arises from expecting a single answer when the situation is inherently ambiguous, when the infinite oscillation resists reduction to a single number. The series continues, 1 minus 1 plus 1 minus 1, terms alternating forever, and the sum is 0 or 1 or 1/2 depending on how you calculate it, depending on what method you use, depending on what question you're really asking. And the paradox endures, a simple series that exposes deep issues about infinity, about summation, about the limits of algebraic manipulation, and about the need for careful definitions when dealing with infinite processes. And Grandie's series remains a teaching tool, a cautionary tale, a reminder that infinity is subtle, that divergent series require special handling, and that mathematics is not just calculation, but interpretation, not just following rules, but understanding when rules apply and when they break down. And the series oscillates, forever unresolved, forever producing different answers, and the paradox persists, elegant and instructive, a monument to the strangeness of infinity and the care required when extending finite concepts to the infinite realm. Gabriel's horn paradox, a three-dimensional solid of revolution, is formed by taking the curve y equals 1 over x for x greater than or equal to 1 and rotating it around the x-axis, and this creates a shape that resembles a horn or a trumpet, wide at one end near x equals 1 and tapering endlessly as x increases toward infinity, growing ever narrower but never closing, extending infinitely far in one direction. And this shape is called Gabriel's horn, named after the archangel whose trumpet signals the end of days. And the paradox is that this infinite horn has finite volume but infinite surface area. And this seems contradictory, or at least deeply strange, because if the volume is finite, then you could fill the horn with a finite amount of paint, but if the surface area is infinite, then you would need an infinite amount of paint to coat the surface. And so it seems that you can fill the horn, but cannot paint it. And this apparent impossibility is Gabriel's horn paradox. The mathematics is straightforward. The volume of the horn is calculated using the formula for volumes of revolution, integrating from 1 to infinity the area of circular cross-sections. And the cross-section at position x has radius 1 over x, and so the area is pi times 1 over x squared. And integrating this from 1 to infinity gives pi a finite volume, meaning the horn could contain pi cubic units of liquid. And the surface area is calculated using the formula for surface area of revolution, integrating the circumference of each cross-section multiplied by an element of arc length. And this integral diverges. It grows without bound as the upper limit of integration increases, and so the surface area is infinite. And this combination, finite volume and infinite surface area, is what creates the paradox. The resolution of the paradox lies in recognizing that paint, as a physical substance, has thickness. It is not a mathematical surface with zero thickness, but a three-dimensional coating. And if the paint has any positive thickness, however small, then painting the inside of the horn requires filling a three-dimensional region, not just covering a surface, and the volume of this region is finite because it is contained within the horn, which has finite volume, and so a finite amount of paint suffices to coat the inside to any specified thickness, and the paradox dissolves. The apparent impossibility is an artifact of treating paint as if it were a zero-thickness mathematical surface, when in reality it is a substance with volume. Another way to see the resolution is to note that the distinction between filling and painting is not as sharp as it seems. Filling the horn means occupying its entire interior volume, while painting the surface means adding a thin layer. But if the layer has thickness, then painting is a form of filling a thin shell around the surface, and since the horn has finite volume, any shell within it also has finite volume, and so painting, properly understood, requires only a finite amount of paint. And the paradox arises from conflating mathematical surface area, which can be infinite, with physical coating, which requires volume, and volume is finite. Gabriel's horn also raises questions about the nature of infinity in geometry, about what it means for a geometric object to be infinite, and whether infinite objects can have finite properties, and the horn shows that they can. That infinite extent in one dimension, length, is compatible with finite extent in another dimension, volume, and this is not unique to the horn. Many geometric objects exhibit similar behavior: infinite regions with finite area, infinite surfaces with finite curvature. And these examples show that infinity is not a single uniform concept, but comes in degrees and dimensions. and that intuitions about finite objects do not always transfer to infinite objects. The paradox also appears in discussions of limits and convergence, because the volume integral converges to a finite value, while the surface area integral diverges. And this difference reflects the rates at which the integrands decrease as x increases. The volume integral decreases like 1 over x squared, fast enough that the sum over an infinite range is finite, while the surface area integral decreases like 1 over x, not fast enough to produce a finite sum. And this distinction between different rates of decay is central to analysis and calculus, determining which infinite series converge and which diverge, which integrals are finite and which are infinite. Some philosophers and mathematicians have used Gabriel's horn to argue about the nature of mathematical existence, about whether infinite objects like the horn really exist or are merely useful fictions, because the horn cannot be physically realized. No physical material extends infinitely, and no physical process could construct an infinite shape. And so, the horn is an idealization, a mathematical abstraction, and the paradox, if it is one, is a feature of this abstraction rather than a claim about physical reality. And this raises the question of whether mathematical paradoxes reveal truths about an independent mathematical realm or merely expose the limits of our abstractions and idealizations. Gabriel's horn has also been used in pedagogy to teach students about improper integrals, about the difference between convergence of volume and surface area, about the importance of careful calculation and the dangers of relying on intuition. And the paradox is memorable. It sticks in the mind, a striking example that challenges assumptions and forces students to think carefully about what integration measures and what infinity means. And for these reasons, the horn remains a staple of calculus courses, a classic example that generations of students have encountered and puzzled over. The horn extends to infinity, narrowing as it goes, its volume contained, its surface spreading without bound. And the paradox asks whether this makes sense, whether an object can be filled but not painted. And the answer is that paint has thickness, that coating requires volume, that mathematical surfaces and physical substances are different, and that the paradox is resolved by attending carefully to what filling and painting actually mean. And the horn remains a beautiful and strange geometric object, a shape that embodies the counterintuitive properties of infinity, a reminder that infinite objects do not behave like finite objects scaled up, but follow their own logic, their own rules, and that intuition trained on the finite is an unreliable guide to the infinite. And Gabriel's horn sounds on, infinite in reach but finite in substance, a paradox that is no paradox once understood, a puzzle that teaches about integration, about infinity, about the relationship between mathematical idealization and physical reality, and about the need to distinguish between what can be calculated and what can be realized, between the abstract and the concrete, between the mathematical and the material. And the horn remains a fixture in mathematics, a lesson in calculus, a paradox that resolves itself once the terms are clarified, once the mathematics is understood, once the nature of paint and surfaces and volume is properly considered. And the paradox fades, leaving behind understanding, leaving behind a deeper appreciation for the subtleties of infinite geometry, and for the care required when reasoning about objects that extend without end. Frankfurt's counterexamples. When you're responsible. Even though you had no choice, a person decides to perform an action, decides on their own, without coercion, based on their own reasons and desires, and they perform the action, and we say they are morally responsible. They acted freely. They deserve praise or blame for what they did. And traditional theories of moral responsibility say that responsibility requires the ability to do otherwise, requires that the person could have chosen differently, that they had genuine alternatives. And this principle, called the principle of alternate possibilities seems obvious, seems essential to responsibility, because how can you be responsible for an action if you had no choice, if you were forced to do it, if no alternative was possible? And yet philosopher Harry Frankfurt constructed examples that challenge this principle. Examples where a person acts on their own, makes their own decision, but could not have done otherwise, and yet intuitively seems responsible. And these are Frankfurt's counterexamples. Thought experiments designed to show that the principle of alternate possibilities is false. That responsibility does not require the ability to do otherwise, that what matters is how you acted, whether the action flowed from your own will, not whether you could have acted differently. And Frankfurt's cases have been enormously influential, have reshaped debates about free will and responsibility, have challenged incompatibilist arguments that say determinism undermines responsibility, and the counterexamples remain controversial, remain debated, but have permanently changed the landscape of discussions about freedom. Imagine the example: a person named Jones decides to perform an action, decides to vote for a certain candidate, and Jones makes this decision on his own, based on his own political views, his own deliberation. No one forces him, no one coerces him, and he goes to vote, and he is about to vote for the candidate he chose. And at this moment, unbeknownst to Jones, there is another person, call him Black, who has been monitoring Jones's brain states, and Black has the ability to intervene, to manipulate Jones's brain, to force Jones to vote for the candidate if Jones shows signs of changing his mind. And Black is prepared to intervene, but does not need to, because Jones votes for the candidate on his own, makes the decision himself, and Black's intervention mechanism remains dormant, unused. And the question Frankfurt asks is whether Jones is morally responsible for his vote. And intuitively, the answer is yes. Jones voted based on his own decision, his own reasons. Black's presence made no difference. Black did nothing, and Jones is responsible just as he would be if Black did not exist. And yet Jones could not have done otherwise, because if he had tried to vote differently, Black would have intervened, would have forced him to vote for the candidate. And so Jones had no alternative, could not have avoided voting as he did, and yet he is responsible. And this shows that responsibility does not require the ability to do otherwise, that the principle of alternate possibilities is false. The structure of Frankfurt cases involves two elements. The person acts on their own, based on their own will, their own reasons, and there is a counterfactual intervener, someone or something that would have prevented any alternative action, that ensures the person does what they do. But the intervener does not actually act, remains dormant, and so the person's action is their own, even though alternatives were blocked. And Frankfurt argues that what matters for responsibility is not whether alternatives existed, but whether the person acted on their own, whether their action flowed from their own will. And in Frankfurt cases, the action does flow from the person's own will, and so they are responsible even though they could not have done otherwise. Visualize moral responsibility as depending on the actual sequence, on how the action was actually produced, rather than on alternative sequences on what might have happened. And in Frankfurt cases, the actual sequence is normal. The person deliberates and chooses and acts, while alternative sequences are blocked by the intervener. And since responsibility depends on the actual sequence, the person is responsible, and the blocked alternatives are irrelevant. And this shows that incompatibilists are wrong to think that determinism, by ruling out alternatives, undermines responsibility, because even if determinism rules out alternatives, as long as people act on their own, based on their own reasons, they are responsible, and responsibility is compatible with determinism. Critics of Frankfurt cases have offered various objections. One objection denies that the person really lacked alternatives, argues that in Frankfurt cases there are flicker alternatives, tiny alternatives, that remain open until the very last moment, moments where the person could begin to choose differently before the intervener stops them, and these flickers are enough to preserve the principle of alternate possibilities, enough to ground responsibility, and so Frankfurt cases do not refute the principle, only show that responsibility does not require robust alternatives, only requires minimal alternatives, tiny flickers of freedom. Another objection questions whether Frankfurt cases really elicit the intuition that the person is responsible, argues that when we imagine the cases carefully, when we recognize that the person truly could not have done otherwise, our intuition of responsibility weakens, and maybe Jones is not fully responsible. Maybe the presence of Black's intervention mechanism, even though unused, affects responsibility, creates a situation where praise and blame are inappropriate, and this response denies that Frankfurt cases generate clear counterexamples, argues that intuitions are unclear or support the principle of alternate possibilities rather than undermining it. A third objection distinguishes between moral responsibility and blameworthiness, argues that Frankfurt cases might show that people can be causally responsible, can be the source of an action, even without alternatives. But this does not show they are morally responsible, does not show they deserve blame or praise, and moral responsibility requires more than being the source of action, requires the ability to do otherwise, requires that the person had control, and Frankfurt cases do not establish moral responsibility, only causal responsibility. Frankfurt has refined his examples over decades, responding to objections, constructing new variants, and the debate continues, with defenders arguing that Frankfurt cases successfully refute the principle of alternate possibilities, show that compatibilism is correct, that responsibility does not require alternatives, and critics arguing that the cases are flawed, that intuitions are unclear, that responsibility does require alternatives after all, and no consensus has emerged. But Frankfurt's contribution is undeniable, has forced philosophers to clarify what responsibility requires, to distinguish between different kinds of freedom, different kinds of control, and to recognize that the relationship between determinism and responsibility is more complex than simple, incompatibilist arguments suggest. Frankfurt's counterexamples also connect to debates about moral luck, about whether responsibility depends on factors beyond our control. Because in Frankfurt cases, the person is responsible, even though whether alternatives were available was beyond their control, was determined by Black's presence. And this suggests that responsibility is not undermined by factors beyond our control, is not sensitive to luck, and what matters is the actual sequence, how the person actually acted, not whether they were lucky enough to have alternatives. Jones stands in the voting booth, marks his ballot, and Black watches, does nothing, and Jones is responsible, is praised or blamed for his vote, and yet he could not have voted otherwise. And Frankfurt's case challenges traditional assumptions, challenges the principle of alternate possibilities, and forces recognition that responsibility is about actual causation, about whether the person's will was effective, not about whether alternatives existed. And Frankfurt's counterexamples endure as some of the most important thought experiments in philosophy of action, examples that reshaped debates about free will, that challenged incompatibilist arguments, that supported compatibilism, and that remain controversial, remain debated, but have permanently influenced how philosophers think about moral responsibility, about what it requires, about whether determinism threatens it, and the counterexamples persist as permanent features of the landscape, cases that every theory of responsibility must address, must accommodate or explain away. And Frankfurt's legacy includes these cases, these examples that showed that responsibility might not require what we thought it required, might not depend on alternatives, but on something else, on source, on causation, on whether the action flows from the agent's own will. And the debate continues, and Jones votes, and Black does nothing, and the question remains whether Jones is responsible, and Frankfurt says yes, and the counterexamples stand, challenging, probing, revealing complexity in concepts we thought were simple.